Okay, students. So now we are going to observe the acids that are present in the lab as well as two acids that we use at home. So you all know what acids are? Substances that release H plus ions in the medium. So and you know the examples. Now here you can see hydrochloric acid, then nitric acid as well as sulfuric acid. And you know the chemical formulae of all these acids. H2SO4 is sulfuric, HNO3 nitric and HCl is hydrochloric acid. Now first look at how they are stored in the lab. Now they are kept inside a brown colored bottle. What is the reason? Because these are very strong acids and usually they are very concentrated. Highly concentrated acids. Therefore, in order to prevent any reactions, they are stored inside brown colored and glass bottles. So the first three are strong acids that we use commonly in the lab. But you all know we can dilute these and use them as the dilute acids as well. Then here I have two more acids. One is the acetic acid here and the lime that also has citric acid. So these two are acids that you can use in the lab as well as we use it for household purposes. And you know those two are weak acids. So hydrochloric, nitric and sulfuric acids are strong acids, whereas acetic acid and lime juice or even orange juice, all these are weak acids. So that is how we identify the acids. And here you can see acetic acid vinegar comes in a plastic bottle. The reason is it is a weak acid and it is somewhat dilute. So compared to the strong acids, the weak acid is not that harmful, especially at the dilute stage. So we can use it for cooking as well. So that is to identify the acid. So we have the concentrated acids in the lab, but we need dilute acids for different purposes. So how do we dilute acids? Do we add water into acid? No. What is the reason? The reason is there will be a lot of heat generated. Due to that, there can be an explosion. It's dangerous. So to avoid that, what we do is if we want to dilute an acid, now let's say I want to dilute the hydrochloric acid here. So I have already taken a small amount of hydrochloric acid into a test tube. Then I have distilled water in the beaker. So if you need to make a certain volume, accordingly, let's say 100 centimeter cubes, you can take about 80 centimeter cubes of distilled water first. Then with the dropper, glass dropper is more better, but you can use this also. Drop by drop, we take the acid and transfer it along the wall of the beaker. So that means the acid will get diluted. Like this, we have to transfer the acid into water. We never pour the water into acid, but instead we have to add the acid little by little into a large container containing water. Here I have taken only a small amount because the acid is only a small amount. But when you are diluting large quantities or large volume of acid, then you will need to use a large container with more volume of water. So that is the acid dilution process. You have to remember that. That is very important. So acids reacts with metal to produce the salt and evolve hydrogen gas. So for example, I have hydrochloric acid here. So this is hydrochloric acid and this is the metal magnesium. So if we put a strip of magnesium, you all know normally the magnesium oxide forms. We have to clean it. Now this part is clean. You can clean it with the sandpaper. So I will break a small piece of the magnesium strip. It's a soft metal, so we can break it easily. And if I put it into acid, you all know the reaction. Magnesium chloride and hydrogen gas will be evolved. So we put it into, you all can see the evolving of hydrogen gas. Here also you can observe. So when magnesium reacts with hydrochloric acid, how do we confirm that the gas is hydrogen? we use a burning splinter, and when you hold it to the gas, you will see the observation. What is the observation? It will burn with a pop sound. So, I will have a matchstick here. I'll put a piece of metal. Carbon dioxide getting bubbled into the lime water, and you can observe the color change as well. Can you all see the solution turning milky in color? You can see the difference between the previous colorless carbonate and dilute hydrochloric acid. It produces calcium chloride, water, and evolves carbon dioxide. So we have confirmed that the gas evolved is carbon dioxide. Okay. Carbon dioxide is bubbled into lime water. So first I will transfer the calcium carbonate into the boiling tube. To that, I am going to add dilute hydrochloric acid. You can observe the reaction, and then we'll need to close it and transfer the gas into the lime water. So here students, you all can observe the carbon dioxide getting bubbled into the lime water, and you can observe the color change as well. Can you all see the solution turning milky in color? You can see the difference between the previous colorless solution and the milky color solution that has formed now. So that is how we confirm the evolving of carbon dioxide gas. So when carbonates and acids react, so here we use calcium carbonate and dilute hydrochloric acid. It produces calcium chloride, water, and evolves carbon dioxide. So we have confirmed that the gas evolved is carbon dioxide. So here students, to identify acids, we use the litmus papers. Here you can see I have the blue litmus and the red litmus papers. I have hydrochloric acid here. So that's one of the commonly used acids. That's why for most of the reactions I use hydrochloric acid. So I'll put a drop of the hydrochloric acid to both the blue litmus and the red litmus. So now can you all observe the color change? The blue litmus turned red, but the red litmus remains the same. So to identify acids, we use blue litmus. Blue litmus will become red. So one of the uses of sulfuric acid is that the concentrated sulfuric acid can be used as a dehydrating agent. Even the gases can be dehydrated or dried passing over sulfuric acid. To observe this property of sulfuric acid, that is concentrated sulfuric acid, inside the test tube I have the concentrated sulfuric acid, and here I have a sample of sugar. So I'll take it, transfer a small amount into the watch glass. Now when I add a small amount of concentrated sulfuric acid, you have to remember students, it has to be concentrated sulfuric acid. When I pour it onto the sample, observe the color change. Observe what happens. Now here you know sugar is a crystalline structure, and what is the chemical formula of sugar? It is sucrose. So it's C12H22O11. So there are water molecules. So when we add concentrated sulfuric acid, observe the changes. It has become light brown in color now. You can see gradually the color becoming darker. I will add some more concentrated sulfuric acid in order to make the reaction a little bit more faster. Now it's turning darker brown in color. So what do you all think will happen? From the sucrose molecule, the sulfuric acid will absorb water. So when you remove from C12H22O11, when you remove the H22O11 component, that's water, what will you get? You will get the carbon. And you all know the color of carbon. So we'll see where the carbon is produced here. Can you all observe the color change there? Little by little in the middle, it's becoming darker and almost turning into black color. Can you all see, students, in the middle, the formation of black color? That is because the water is absorbed by conc sulfuric acid, concentrated sulfuric acid, and only the carbon will remain. It takes a little time. Now similar to this, now this is a tile, if this was wood like in your school labs, if you spill concentrated sulfuric acid from the wood, sulfuric acid will absorb water, so only the carbon will remain. So that is also another activity. You can take a small piece of wood and onto that you can pour a little amount of sulfuric acid. It has to be concentrated. Then it will become black in color. That's because after water is absorbed, only the carbon will remain. Now you all can see the change clearly. So what is in the middle? The black color is carbon. So you can see initially the sugar was like this and now it has become, or it's turning into black color. So now we are going to observe the bases that we have in the lab. So here I have a sample of sodium hydroxide, a sample of potassium hydroxide and calcium hydroxide powder. Now in all these you can see the OH. So any substance that increases the hydroxide ion concentration, that is OH minus ion concentration in the solution, is a base. And in that you all know, if it dissolves well in water, it's an alkaline solution. So out of those, there are strong bases and weak bases. So what I have here, sodium hydroxide, potassium hydroxide and calcium hydroxide, all these are strong bases. And sodium hydroxide is one of the very common bases that we use in the lab for many activities. And you all know it dissolves well and produces sodium hydroxide solution. So these are the strong bases that are available in the lab. Can you all think of an example for the weak base? Ammonia gas. Normally bases are solids. They are in this pellet form. But ammonia gas is a base that is present in the gaseous state. And when you bubble ammonia into water, the ammonium solution, that is ammonium hydroxide, is a weak base. Similar to that, there are substances that we use at home. Caustic soda, washing soda, these are all basic substances. Even soap that we use in our day-to-day life, they are all bases. And there again, depending on the type of base, it can be a strong base or weak base. But you all know, since we touch and use soap, it has a weak basic property. So students, like identifying acids, we can use the litmus papers to identify bases as well. So here again, I have the blue litmus and the red litmus paper, and I have prepared a solution of sodium hydroxide. So it's an alkaline solution. Why? Because it dissolves well in water. So here, and it is also a strong base. And students, since this is a tile, there's no problem. I can place the litmus paper on the tile, and on that I will put a few drops of sodium hydroxide. So here you can observe the color change. You can see. The red litmus completely turns blue. You can see the color change. Whereas the blue litmus remains the same. So, using this, you can easily identify bases. But here, you cannot use the litmus paper to identify whether it's a strong base or a weak base. We can only identify whether it's a base or not. So, red litmus becoming blue color means it is a base, or the bases turn red litmus to blue color. So, one of the uses of sodium hydroxide is the production of soap. So, normally you all know there are so many different types of soaps with different fragrances, different colors. But the basic soap, the component, can be prepared using these materials in the lab. So, for that we need coconut oil. I have here 40 centimeter cubes of coconut oil, 40 centimeter cubes or 40 milliliters of coconut oil. With that, I need to have 40 milliliters or 40 centimeter cube of sodium hydroxide solution, the same volume. So, to do that, I have 10 grams of sodium hydroxide measured here and the required amount of water. So, what I am going to do is, I am going to transfer the sodium hydroxide into this and dissolve it completely, so that we get the sodium. Here you can see, students, normally sodium hydroxide bases become slimy. You can observe that slimy nature here. In this, you can observe the slimy nature. They become a little like watery, like mainly slimy. So, then if we dissolve it well, you can see the sodium hydroxide, the pellets dissolve well. And you all know when we dissolve it, there is heat evolved. The beaker, I can feel it, it's warm. So, when bases dissolve in water, they evolve heat. So, now that I have the sodium hydroxide solution ready, then I have to heat this oil to 70 degrees Celsius. That is what I am going to do next. We don't boil it, we don't bring it to the boiling point, but we heat it to 70 degrees Celsius. I have the coconut oil in a 250 milliliter beaker because it will be easy to transfer the sodium hydroxide and mix it well. So, now you can see the burner. So, the oil has to be heated to 70 degrees Celsius. You can see in this, initially the temperature, it's around 30 degrees. So, you can see, students, the temperature when the oil becomes hotter, the thermometer reading will rise. We have to bring it up to 70 degrees Celsius. So, we shouldn't touch the beaker, then it will be the temperature of the beaker, not the temperature of the oil. So, I am just touching the oil only. So, now you can see, students, the temperature, the thermometer reading is 70 degrees. So, I can move the thing and switch off the burner. So, that now we don't need the, so I can remove the beaker from the right. So, here we have the oil at 70 degrees Celsius. Now, little by little, I have to add the sodium hydroxide solution and mix it well, so that the reaction will take place. And this mixing has to be done continuously for about 15 to 20 minutes. And when we mix, you can see the change, the pasty-like nature of soap appearing. So now, because it was not brought to boiling point, I can touch the beaker. There's no problem. It's still warm, but still I can touch the beaker. And to this, you all know we can add fragrance as well as we can add color. So here I am not going to add any fragrance. It will be the normal soap, but to see the soap clearly, the color, I will add phenolphthalein indicator. So here we have phenolphthalein indicator. You all know it will give a pink color with bases. So a few drops of phenolphthalein indicator, you can see the color. So that is to indicate it's the base, and also when we mix it together, the soap will become pink in color. Now the base is reacting, that is why the color disappeared. So after some time, if I add it again, we will get the basic color. You can see then before, now the mixture is becoming paste-like, more thick. So here students, you can see I have been mixing it for about 10 minutes. So now you can see then from earlier, the mixture has become paste-like. You can observe that clearly here. It's a pasty-like nature. That's because the coconut oil is reacting with sodium hydroxide and the soap is forming. Like this, I have to keep on mixing for another 10 minutes. Okay students, so now with about 20 minutes of mixing, now you can see the pasty nature of the soap. So to this, I am going to add food coloring to give the color. So this is a few drops of the color in order to, so that you can observe the soap. So now here you can see it's more pasty like, and then I will transfer it into this mold here. You can use any shape. If you all are trying this at home, you can even use those molds with different shapes. Sometimes what you use for the jelly mold, anything can be used, or even a yogurt cup. So now we will have to leave it aside for about 12 hours. So with that, the soap will solidify. So what did we add here? We took 40 milliliters of coconut oil and 40 milliliters of sodium hydroxide solution. The coconut oil was heated to 70 degrees. Then I transferred the sodium hydroxide, mixed it well for about 15 to 20 minutes. Now after 20 minutes, you can see the pasty soap mixture is there. So now we need to leave it aside for 12 hours so that it will completely solidify. So I will show it to you all after 12 hours. So first I explained to you all how you are supposed to prepare the soap. Then I told you we have to keep it aside after pouring the soap mixture into a mold like this. We need to keep it aside for about 12 hours. So this is a soap that I have already prepared. I have already left it aside for 12 hours. So here you can see it has solidified. So when we just touch it also, if I can really feel the slimy nature of it as well. So that means the sodium hydroxide has reacted completely with coconut oil and it has solidified also. So that means it has been converted into soap. But the thing is students, this is just the raw basic substance that we use as soap. But the soap that you all use at home, that has a fragrance added to it as well as a color. So with that, it has other substances in it. So because of that, you get the nice smooth texture, the shape of it, fragrance, everything is there. And also sometimes they increase the value. Some are medicated like that. There are various types of salt. But the basic is this. You need to react the coconut oil with sodium hydroxide. So one of the uses of sodium hydroxide. So you can observe that here. So now we are going to use indicators to identify acids and bases. You all know what indicators are. They are substances. Either they can be in the form of a paper. You all are familiar with the blue litmus and the red litmus. Already we used it to test the acids and bases as well. And in addition to that, I have the two solution indicators, liquid indicators. Here you can see this is phenolphthalein. That is a colorless indicator. It's a colorless solution. And inside this beaker, you can see the methyl orange indicator. As the name implies, it's an orange color solution. So these are solutions that can be used to identify the acids and bases. So to identify them, I have a few samples given to you here. The first one is dilute hydrochloric acid, lime juice, sulfuric acid, vinegar. So you know these are all acids, and out of these, dilute sulfuric acid and dilute hydrochloric acids are acids usually available in the lab. Lime juice and vinegar are usually used at home. And we have dilute sodium hydroxide, the base commonly used in the lab, and soap, that again is a basic solution that is used at home or available at home. So now we are going to test and see how these indicators give color with these acids and bases. So for that, first I will start with the litmus papers here. So I have arranged a set of litmus papers, both the blue and red for all the solutions. So I will put a drop of the solution to the litmus paper. And students, again here this is a tile surface. So directly I can place the litmus papers there and put the solution on it. So no problem. So first I'll start with the dilute hydrochloric acid to the red litmus and the blue litmus. You can observe the color change there. Then the second one, I will put a drop of lime juice to the red as well as the blue litmus. Then sulfuric acid again to red and blue litmus papers. Vinegar to both red and blue litmus. So now you know the four solutions. Now can you all see the color change? The red litmus remains the same and the blue litmus is turning to red. So acids turn blue litmus to red. That is one observation. Then here I have the base solution, sodium hydroxide to red litmus and to blue litmus. Now you can see the color change there. So this is the soap solution. A drop of soap solution onto the red litmus and to the blue litmus. So here you can see. Now sodium hydroxide is a strong base. So immediately, if you have been observing closely, immediately the color change. But with the soap solution, you can see it's taking a little longer time. But still, you can see the color change. Only where the air bubbles are, there's no change. But where the solution, soap solution is, you can see that the red litmus has become blue in color. So with bases, the red litmus becomes blue. But the blue litmus remains the same. With acids, the blue litmus becomes red. So here you can see all the acids. Dilute hydrochloric acid, lime juice, sulfuric acid and vinegar. All of them, the color of the litmus paper is red. dilute sodium hydroxide, and soap, the color is blue. So now can you all understand how the litmus paper gives color to these acids and bases? So using the two litmus papers, red and blue, we can identify whether a solution is a base or an acid. The same way, now I told you all about the indicators. So this is the phenolphthalein indicator. It is a colorless solution. So here again I have the same solutions in order. This is the dilute hydrochloric acid, then the lime juice, dilute sulfuric acid, vinegar, dilute sodium hydroxide, and the soap solution. To all these I am going to add a few drops of phenolphthalein indicator. Now to this, the phenolphthalein indicator into all the acids. So phenolphthalein to the acids, then I'll add phenolphthalein to the bases. This is sodium hydroxide and that is soap solution. So here you can see the color of sodium hydroxide, that is dilute, and also the soap solutions. In both it turns to pink color, like a purplish pink color solution. So phenolphthalein indicator is usually colorless. In a base it turns from colorless to pink. But in acids, it remains the same. It's a colorless solution in acids. So you all can observe the changes clearly. So similar to these students, I told you all about the methyl orange indicator. You can see the color itself is methyl orange. So I am going to add few drops of methyl orange to the same solutions. Dilute hydrochloric acid, lime juice, dilute sulfuric acid, vinegar, dilute sodium hydroxide, and soap. Right. So now I am going to add these indicators. Methyl orange to acids. Now you can observe the color change. It is becoming red in color. And then to bases. So now here students, when I mix it, you can see the color changes. So now with the acids, can you all see the color? From orange, it has turned to red. Actually, it looks like pink or pinkish red. So normally we say from orange, it turns to red in acids. So methyl orange gives yellow color with bases but turns red with acids. Phenolphthalein gives pink color with bases, remains colorless with acids. And again, the litmus, red litmus becomes blue with bases, blue litmus becomes red with acids. So those are the indicators. Now from all these, you all know HCl, sulfuric acid, those are strong acids. Vinegar, lime juice, weak acids. Is there a difference in the color change? There is no difference. All these give red color with blue litmus. Same way, sodium hydroxide is a strong base whereas soap is weak. But still you can see the color change is similar. Here also the same. So from all these indicators, we can only identify whether a solution is an acid or a base. But we cannot determine whether it's a strong acid, weak acid, or strong base or a weak base. So for that, we will be using another type of paper. We will be discussing it, that is the pH paper. So now we are going to observe how pH scale works with the acids and bases. So you are familiar with these two papers. What are they? The red and blue litmus papers. And you all know how the color changes. Bases, it's blue color. For acids, it becomes red in color. So that is already what I did. I have it still here. So now I have here the pH paper. You all can see the difference, students. Now these two, blue and red, whereas this is a yellow color strip of paper. Apart from that, they all are similar. So again, we use it to identify the acid and bases. Now this also comes in a booklet like this. Here you can see, and here you can see the numbers. Those are the pH values. You all know about pH scale, students, from 1 to 14. But here they have skipped the numbers 1, 3, 5. Then you have 6, 7, 8, 9, 10, 12 and 14. But the scale continues from 1 to 14. And you can see how the color changes. So to show you all the color change clearly, I have this printed pH scale. This is there in your textbook as well. You can see they are both similar. The pH scales are similar. Can you all see that? So this is more easy to observe the colors. So again, as I did before, I have strips of pH paper placed in front of the solutions that we are going to test. Now here dilute hydrochloric acid, lime juice, dilute sulfuric acid, vinegar, dilute sodium hydroxide and soap water. So from each solution, I am going to put a drop on the pH paper. So now you can see the color changes. I will add all the drops and then we will discuss the colors. Here again, the vinegar solution, sodium hydroxide and soap. Now we'll wait till the color changes completely. Now can you all see a difference here, students? Now this dilute hydrochloric acid and dilute sulfuric acid, the color is more darker. So if I bring the paper here and compare, can you see the colors? It's almost between 0 and 1. We can take the pH range as 1. Can you see here the pH scale? We can take it as 1. But if we take the lime juice, then can you look at the color? It's somewhere between 1 and 2. So that means it's not very dark as the HCl and sulfuric acid. So can you all look at the colors? Can you compare the colors? So you will see that the pH scale is somewhat different. So it's almost towards pH 2. So now can you all get an idea? Then I'll bring it closer to the vinegar. Now see the color. This is almost 3. Now the color is different. Different from sulfuric acid and hydrochloric acid. So the pH is 3. So from the scale, we can read that hydrochloric acid and sulfuric acids, they are strong acids. So they show a pH either 0 or 1, sometimes 2 also, towards 2. But when you take the weak acids, they show pH values between 2, 3, even 4, 5 up to 6 is the acidic pH. So starting from 0 up to value 6, it is the acidic pH. Strong acids have the lowest value. So when the pH value increases, the acids become weaker, or we can say the acidity decreases. So when you go from 0 to 6 in the pH scale, the acidity decreases. The same way, now we will look at the two bases. Now can you see sodium hydroxide? It's the same color as pH 14, a very strong base. So can you all see the color? It's clear to you all. Then look at the soap. Now this is almost between 12 and 30. So it's weaker than sodium hydroxide. Although we use sodium
hydroxide for the production of soap, but as soap the pH is less. So here going from 8 to 14 it is the basic pH, and there when you go from 8 to 14 the basicity increases. You all can observe that clearly. So unlike the litmus papers, pH papers gives us an indication about the pH value of the acid as well as the base. So we can easily compare and understand which is a weak acid, what is a strong acid, or weak bases, strong bases, all that can be understood. So again, to go through the pH scale, I told you all from 0 to 6, it's the acidic pH. Then 7, I didn't mention 7 before. That is the neutral pHs at 25 degrees Celsius. So let's say if you take distilled water, that will show a pH of 7. From 8 to 14, it is the basic pH and the basicity increases. So from 0 to 14, acidity decreases, basicity increases. Is that clear to you all, students? So now you all have observed the color changes also. You will understand the use of pH scale in order to identify acids and bases.